F5. F5.
No, go to.
See the little on the bottom where it has 75%. Click on that little. Click on that.
This little icon here, or if you just hit F5, it'll take you to the presentation.
You're doing all right? Yeah.
There you go.
Hit that little bump. Just hit the enter key.
The enter key?
Yeah. There we go.
Okay, that's advanced.
Okay.
Just hit
Page
down.
down.
Yeah, in fact, I can help you if you want. Just tell me this one.
That's okay.
You sure?
Yeah. You should, okay.
See it page down?
Yes.
Yeah. The
Down there on the
the
right hand
arrows.
side.
Down there.
Okay,
Yeah,
this
right
one
there. Yep.
Okay. Good. Okay. Well, thank you very much for helping. Thank you for coming this morning. I want to just talk a little bit about the U.S. chemical infrastructure, and hope that in my presentation today you'll be able to come away with some understanding about how it works, and also in terms of the importance of the infrastructure itself, both to our society in general, and I have some slides at the end which illustrate, I think, some of the importance to the U.S. military. The U.S. chemical infrastructure is the largest in the world. It's over $4 billion in value, and it has been the largest in the world probably since around 1900. With chemicals, we're basically taking raw materials, and these can be gases, as in the form of a pipeline. They may be very large quantities of liquids and solids that come in ships and barges. Very commonly, they're moved by tank cars and trucks, and in some cases for solids, they will be moved in hopper cars. So you take these materials in their various forms, and you put them into some kind of proverbial black box, some kind of processing, and out the other end comes other stuff. And again, it can be shipped by pipeline, ships, barges, tanks. Some of it gets shipped in smaller quantities like drums, and some will be sent to intermediate storage where it ultimately gets shipped out. That's just a kind of a logistics type of scenario. From there, the products, the chemicals, as they are, can go to other chemical processing, or they can go for use in other manufacturing. When we talk about internal dependencies in the chemical industry, we're talking about a chemical that's produced by one company now becomes the raw material for another. So you see, for example, here, sulfuric acid, the largest inorganic chemical produced in the world, is used to extract phosphoric acid from phosphate rock. So you're taking the liquid, mixing it with a solid, and you're actually going to come out with phosphoric acid. That's one way of making phosphoric acid. Now, in the case of like nylon, okay, nylon starts out as benzene and propylene. Now, DuPont is one of the largest producers of nylon in the country, but it doesn't produce benzene and doesn't produce propylene. Those are usually produced by companies such as ExxonMobil, perhaps Chevron Phillips. Chemical companies also depend upon the services and products of an infrastructures. So, for example, if you take caustic chlorine, you need an inordinate amount of electrical energy to produce caustic soda and chlorine. The same is true of aluminum. One of the reasons why, at least at some time, much of aluminum production in the United States was located up in the state of Washington or the Pacific Northwest because of the prevailing amount of hydroelectric power at low costs. In the case of ammonia production, ammonia relies on natural gas. One of the reasons why, for example, ammonia production is readily available in Trinidad is because they have relatively cheap natural gas prices. There is ammonia production in the United States, and it is dependent upon natural gas, excuse me. So again, these are external dependencies on which the chemical industry depends. Now, these are external dependencies of other infrastructures on the chemical industry. The one on the upper left is natural gas sweetening plant. And there you use, say, what they call ethanolamines to extract the sulfur. That's what they call the sweetening process, the removal of the sulfur from the natural gas so that eventually it ends up as a fuel that many of us probably use to heat our homes. The upper right one is a hydrofluoric acid alkylation unit. Alkylation is a process by which they basically make a component used in a high-octane gasoline. And we use the hydrofluoric acid as a catalyst in that process. The hydrofluoric acid is actually quite dangerous. It's one of the chemicals that is on the EPA's risk management program list as a seriously dangerous chemical. Lower left, we're talking about water treatment. It could be also wastewater treatment. Very heavily dependent upon chlorine, perhaps even sodium hypochlorite. Some companies are going away from liquid chlorine and using sodium hypochlorite because it's a lot safer. And on the lower right, sulfur hexafluoride is used as a dielectric in high voltage circuit breakers. One of the unique things about chemicals is, unlike electric power, which can transmit over wires, is that all chemicals have to be physically transported. So you can, for some commodity type chemicals, such as hydrogen, oxygen, nitrogen, and they do this with propylene and ethylene, you can transport it by pipeline. There's a huge network of pipelines going from the Texas area all the way over to Louisiana, which transports, I know, propylene and ethylene. There are pipelines that transport ammonia from the port of New Orleans up into the Midwest. Much of that ammonia is used for direct fertilization. And of course, the roads are heavily used for transport of chemicals in bulk. So that's a very big interdependency dependency that the chemical industry has on transportation. Same is true of railroad. When it comes to barge traffic, a lot of chemical plants are situated along large rivers, and that's so as in some cases they can move large quantities of chemicals from ports of delivery or in between themselves. If you were to go down Mississippi River from Baton Rouge all the way to New Orleans, there's probably not a chemical company in the world that doesn't have something along the river there. We're going to get into here a little bit of the what I call the military dependencies on chemicals. I just want to clarify some points about chemical versus a chemical product. A chemical would be, for example, like a chlorine or an ammonia. A chemical product would be either perhaps a mixture of chemicals, and then of course there's also chemicals that are used to make other products. I just hope to clarify that here. Now this slide here, we're talking about CARCs, which stands for Chemical and Agent Resistant Coatings. CARCs are the largest category of paints applied to U.S. military equipment. It includes not only these track vehicles, but also, as I understand, artillery pieces and missile launchers and things of that nature. A key chemical in CARCs is the hexamethylene diisocyanate, and there's also some other solvents that actually go into it as well. Body armor to protect our troops. Kevlar is a chemical product Boron carbide is also used as a kind of like a it's hard ceramic that's been used in tank and body armor, and it's important. These are chemical products that are made from chemicals that are important for the use of our U.S. military. This is a particularly one that's close to me because when I was on the Navy, I stepped in some freshly applied non-skid on the flight deck. My shipmates were not happy, so I was thrown over the side. And a carrier flight deck has about 4.5 acres. It's covered with all of this stuff, and typically the ingredients up here are what goes into making this non-skid, which is kind of like a kind of very thick kind of paint with this very coarse material inside, probably created by the aluminum oxide and some other things. Would mention also that titanium dioxide is one of the largest produced chemicals around, and it's heavily dependent upon chlorine for its production. HFCs, or hydrofluorocarbons. Two examples of this are tetrafluoroethane, which is HFC 134A. It's used as a refrigerant on Navy ships. Halon used to be used on Navy ships, and now they're using a heptafluoropropane in their fire suppression systems. Liquid oxygen, liquid nitrogen, used on aircraft. Liquid oxygen for life support systems, liquid nitrogen for tires and struts. Also, the radar units on aircraft like this are cooled with what they call polyalpha olefins. There's a chemical product called Status 450. It's a static dissipator. It's the only approved anti-static dissipator approved in U.S. Air Force fuel, the JPA. And that concludes my presentation. Thank you.
Douglas, thank you very much. And again,